v to the minus 0.28, that is one added to the exponent, divided by the new exponent, 0.28, and evaluate it from 0.03 to 0.04. Alright. We have 115 divided by a minus 0.28, and then we're going to evaluate 1 over v to the 0.28 power, so divided by that denominator, made it positive, and evaluate that from 0.03 to 0.04. Okay, now we can go ahead and plug in the limits. We have square root both, so this is equal to 115 divided by minus 0.28 times. I plug in the other limit, I get 1 over 0.04 raised to the 0.28 power, minus 1 over and 0.03, because that's the near limit, and raised to the 0.28 power. Good thing we have calculators, because without calculators that would be quite difficult to do. So, how do we do that? Well, let's start with the one in the back. We get 0.03 raised to the 0.0 power. So take the inverse of that, and then we put a negative sign in front. Okay, so now we're going to subtract that from plus 0.04 raised to the 0.28 power. Take the inverse of that, and now equals. So this whole thing, let me write down what that looks like. So we get 115 divided by a negative 0.28 times a negative 0.2066. So in case you want to try this yourself with your calculator, that's what you should get for what's inside the brackets. So now we multiply times 115 and divide by 0.28 negative equals, and that tells us then that the work done is going to be equal to 84.8 joules. And again, that's the work done by the gas expanding from 30 meters to 40 meters under these conditions. So that's how you do a problem like that. Again, you need to find a relationship between pressure and volume. In this particular case, it's T e to the gamma equals some constant. Then you realize that the gamma in this case, because the tight on the gas is 1.28, we know that the work done is equal to pressure times dV. The pressure needs to be replaced by the function in terms of volume. So we did that here. Then we go ahead and integrate and put in the limits. And that's how it's done. I should have picked a better constant, but hey, good enough. Now let's do the problem we did on the previous video again, but with a different method. Remember the answer we got? The amount of work done to empty the semi-spherical tank that has a radius of 5 meters was going to be 8 million, just under over 8 million joules, 8.02 times 10 to the 6 joules. But we can also do it as follows. The work done to move all the water out of that tank is equal to the mass of the water times G times the distance we have to move from the center of mass of that water in the tank to the top. So what we need to do is find the center of mass, which is probably a little bit closer to the bottom than to the top. So let's say it's about right there. We need to find this distance right here, y center mass, and after we find this distance here, then it becomes really easy to find the work done to empty out the tank. So let's go ahead and do that. First, this is the easy part. Let's calculate the mass of the water in the tank. So we know that the mass is simply equal to the density times the volume, and since it's a semi-sphere, that would be equal to the density times half of the volume of the sphere, which is 4/3 pi r cubed. Of course, we can simplify that a little bit, so the mass is equal to density times 2/3 pi r cubed. So now we already know G, mass, now we need to find the distance to the center mass, from the top to the center mass. Okay, how was that done? Again, what we're going to do is we're going to take a little slice, and we're going to say that the distance to the center mass, and the distance is right here, so let's call that, let's see, what should we call that? How about this center mass, distance in the y direction, is equal to the integral of all the dn's multiplied times the distance to that dn. So the Lyapunov, we call it, divided by the sum of all the mass. Now this, of course, gives you the mass of the semi-sphere, the water in the semi-sphere, which we already know. Now we have to solve for the numerator. So this is equal to the integral from 0 to 5 of dn and dm of a slice. Okay, so the way we find it is we find the dv, like we did in the previous video, which is equal to this. And now dm is equal to the density times dv, which is equal to the density times pi times 25 minus y squared dy. So this is simply the density times the volume, and the volume is defined as the cross-sectional area times the height. The cross-sectional area is pi r squared dy. Instead of writing x squared, since we know that x squared plus y squared equals r squared, we can then write, well, 25 minus y squared, or simply, let's just keep it as r squared minus y squared. Let's write this as r squared minus y squared, and then let's make our limit from 0 to r, and it's possible to do it in a more general sense. Alright, so now we're able to multiply the dn, which is that, so density pi times r squared minus y squared dy, multiply times the distance from the bottom to that, because the center mass is right inside the slice, so multiply times y, and divide this by the mass, which we know is going to be 2/3 times the density times pi times r cubed. Well, notice that we can already cancel out the densities and the pi's and divide by 2/3, same as multiplying times 3/2. And let's see here. So this becomes equal to, the limits are from 0 to r, of r squared y minus y cubed. I'm multiplying this y times the two terms in here times dy. We can integrate that from 0 to r and divide that by what we have left, which is 2/3 r cubed. Okay, now let's go ahead and integrate that. This is equal to r squared y squared over 2 minus y to the 4th over 4. Evaluate it from 0 to r and then divide that by 2/3 r cubed. Given the lower limits, we get nothing, because 0 here is a 0. Given the upper limit, we get the following. We get r squared times r squared, which is r to the 4th divided by 2, minus r to the 4th divided by 4. The whole thing divided by 2/3, r cubed. So r to the 4th divided by 2 minus r to the 4th divided by 4 is r to the 4th divided by 4, divided by 2/3 r cubed. Notice that the r cubed goes into r squared just 4 times. And we have 1 over 4 divided by 2/3, which is going to be 3 over 8. This is the distance from the base of that semi-spherical tank to the center mass. This distance right here, we call that CMY. That's this distance here, CMY. What we want is to run YCM, which is 5 minus that distance. So we can say that YCM, the distance from the center mass to the top, is going to be equal to the total 5 minus what we find here, which is 3 over 8R. And that's what goes in here. So now we're ready to find the work done, and hopefully we'll get the exact same answer as before. So now we know that the work done is equal to the mass of the water times g times the distance we have to lift the water from the center of mass to the top of the tank. So the mass, we know, is going to be, let's write down the equation, so mg times ycm. That's equal to the mass, which is 2/3 times the density times pi times r cubed. Multiply that times g, and then multiply times YCM. Now YCM is found to be 5 minus 3 over 8R. Now remember that in this case, R, the radius of the tank, is equal to 5 meters. So we can actually replace everything, every R by 5. So to replace this by 5, we have 5 minus 3h times 5, which is 5h, which is 15h. So we can say that this is equal to 2/3 times the density times pi times R cubed, which is 125. That's 5 to the third power, times g, 9.8. So here we have 5, 3h, 5 times 5, or 5 minus 3h, 5, which is 5h, 5 times 5 is 25 over 8. 25 over 8. Okay, now we're ready to find the answer. So 2 divided by 3 times the density, which is 1,000 kilograms per cubic meter, times pi times 125 times 9.8 times 25 divided by 8 equals, and yes, we get the same result of 8.02 times 10 to the 6th joules, or just over 8 million joules to empty the tank by pumping all the water out the top. So here, it's a different method. The way we did it was to find the center of mass. It's right here, and I'm realizing that if we take all the mass of water in the tank and lift it from the center of mass to the top, using this equation right here, we can find the exact same result. And that's how it's done. Welcome to our lecture online. It is really interesting that we can actually write trigonometric functions like the cosine and the sine in terms of complex exponentials. Well, here we're trying to show that the cosine of x can be written like this, and that the sine of x can be written like this. So let's see how that came about. First of all, what we can do is we can expand these two right there. We can say that e to the ix plus e to the negative ix is equal to, well, expand this one, it becomes the cosine of x plus I times the sine of x. And then what we can do is add to that the expansion of this, which is the cosine of x minus I times the sine of x. So now when we add those two together, let's see what we get. Well, the cosine of x plus the cosine of x is equal to twice the cosine of x. But notice that I sine of x minus I sine of x cancels out. So now we have e to the ix plus e to the negative ix is equal to twice the cosine of x, which means when we divide both sides of the equation, we can write that the cosine of x is equal to e to the ix plus e to the minus ix divided by 2. Just what they asked us to do. And we can do the same thing for the sine of x. So what we can do is take the numerator here and expand it and see what we get. And so we can write that e to the ix minus e to the minus ix is equal to, well, this will expand to the cosine of x plus I times the sine of x. And now we subtract from that when we expand this. And this becomes the cosine of x minus I times the sine of x. Now we realize when we combine those two, That's the cosine minus the cosine. The cosine of x cancels out, but the I sine of x does not. Because this negative makes that negative into a positive, so this becomes equal to 2 times I times the sine of x. And then we'll write this down, e to the ix minus e to the minus ix. If we now divide both sides by 2i, then we get sine of x is equal to this divided by 2i, or sine of x equals e to the ix minus e to the minus ix, all divided. Combine the sine of x and the cosine of x in terms of complex exponentials, and that's how it's done. Welcome to our lecture online. In this example, we're going to lift the water out of the semi-spherical tank. Notice that the height is 5 meters, therefore the radius is 5 meters. And what we're going to do again is take a small slice, find the volume of that slice, find the mass of that slice, and then find the work required to take that small slice out of the tank. And then we're going to integrate over all the slices to get the total work done to lift all of the water out of that tank. It's a semi-spherical tank. So the VV, the small volume, it's going to be like a flat little washer. Well, it's not really a washer because there's no opening. So slice, small little slice, VV, it's going to be the area times the height dy. And the area would be the area of the circle. And notice that if we draw an axis in here, call this the y-axis and call this the x-axis here. This is the y-axis. Notice that this would be the distance y to that slice. And here, this would be x. So the area of that would be pi r squared or pi x squared. So this is pi x squared dy. Now, we have an x squared and a dy, so we need to somehow change the x squared in terms of y. But since this cross-sectional area here is a semicircle, we can then take this distance r here to the edge. Y would be the height, x would be this, so we can write that x squared plus y squared equals r squared. In this case, r is 5, so it would be 25 squared, or x squared can be written as 25 minus y squared. And we can substitute that in here, so the volume of the slice now becomes pi times 25 minus y squared times dy. Okay, now, to find the mass of that, we can then say that dm is equal to the density times dv, so this would be equal to the density times pi times 25 minus y squared dy. And finally, to get the work to lift that smaller dm up to the top, notice that the distance here would be 5 minus y, so then the work done, dw, would be equal to dm times g times the height that we lifted through, which would be 5 minus y. That would be the work done to lift the small little slice to the top, and therefore the total work done is equal to the integral of all the little w's. We're going to integrate from y equals 0 to y equals 5, and so this is going to be equal to, let's take all the constants out. Well, anyway, dn is equal to that. Let me just write it down first. It's going to be the integral of dm, which is the density times pi times 25 minus y squared times dy. So the dm is this quantity right here, multiplied times c, and multiplied times 5 minus y. Okay, we have everything now we need to integrate, but we probably want to pull out the constants. Density, pi, and g, and multiply this times this, so the limits would be from 0 to 5. So this would be equal to density times g times pi, times the integral from 0 to 5. Multiply this together, we have 25 times 5, which is 125. We have 25 times a minus y, which is a minus 25y. We have a 5 times a minus y squared, that's minus 5y squared. And then we have a minus y squared times a minus y, which is plus y cubed, all times dy. And remember, that will be the total work done to lift all the water out of that semi-spherical tank. Let's go ahead and integrate that. So work done is equal to density times v times pi times 125y minus 25y squared over 2 minus 5y cubed over 3 and plus y to the 4th over 4, evaluated from 0 to 5. Now notice when checking the lower limits, we get 0, so we don't have to worry about that. Now we need to plug in the upper limit. So this is equal to density g times pi, so this right here. And we're plugging 5. Here we get 125 times 5, which is 625, minus 5 squared is 25 times 25 is 625 divided by 2. Plugging this, we get 5 cubed, 125 times 5 is 625 divided by 3. And then plus the last term, 5 to the 4th is 625 divided by 4. So notice I can pull out a 625. So this means that work done is equal to density times v times pi times 625. And we have remaining 1 minus a half minus a third and plus a fourth. Now here the common denominator looks like it's going to be 12. Yes, 12. So that means that this is equal to density times g times pi times 625 times. So this would be 12 twelfths minus 6 twelfths minus, what would it be? That would be 4 twelfths and plus 3 twelfths. This would be 12 minus 6 is 6, minus 4 is 2, plus 3 is 5 12. So this is equal to density times G times pi times 5 times 625, which is 3,125. And now divide the whole thing by 12. And work done equals, let's go ahead and calculate that out. So we have 1,000 times 9.8 times pi times 3,125 divided by 12. And that gives us 8.02 times 10 to the 6th. So joules goes 10 to the 6th million, so just slightly over 8 million joules to empty out that semi-spherical tank. Again, the method is, find the slice is dV. When it's in terms of x squared dy, we have to then relate x to y. We do that using x squared plus y squared equals r squared. And replace x squared by 25 minus y squared, since r squared is 25. Then dm is going to be the density times the volume. Then we can go ahead and find the work done by saying that the work done is equal to mass times g times the height to which we have to lift it. It will be 5 minus y, which will be the height each line which we lift it by. Then we have to integrate that, and there's the results. That's how we should. In the previous several videos, we saw that when we have two objects revolving around the barycenter, we can actually determine their relative masses by detecting their Doppler shifts, therefore their relative velocities, and also we can then understand their relative radii. But what happens if we have the case where the mass of the large object is much, much greater than the mass of the small object in such a way that R1, distance from the barycenter to the center mass of the large object, approaches 0, and therefore the distance of the small object to the barycenter is roughly the same as the distance from the small object, the center mass of the small object, to the center mass of the large object. So essentially, the velocity around the barycenter of the large object becomes virtually 0, and so how do we determine the velocity of the small object, and can we find some sort of mass relationship here? And the answer is yes, we can, by using Newton's law of gravity, and also realizing that for any object revolving around another object, and then in this case, the small object does indeed revolve around the large object, since the barycenter is virtually the same place as the center mass of the large object, we can then assume that the force of gravity equals the centripetal force. So what we can then write is that the force of gravity on the small object, because of the pull of the big object, must equal to the centripetal force. And Newton's law of gravity tells us that we have G times m1 m2 divided by the distance between them, which in this case would be r squared, which is the same as r2 in this case. And that would be equal to the centripetal force, which is equal to m v squared over r. Now in this case, that's the same r because it's the radius of the moving object, and it would be the velocity of the small object, so we call that v2 squared. So let's make this message as scale factor with respect to the conformal time squared times this. And so you recognize that we define conformal time as obeying to d eta equals to x over a. If I'm rigorous in my notations, I will try to use only the prime for the derivative with respect to conformal time, and the dot for the derivative with respect to proper time, cosmological time. The time in which, at the background level, I get the 1 here, or a g squared if I'm not in natural units. Okay, the other parameter is, as you know, a dot over a. So in terms of conformal time, it's a prime over a squared. Since we are talking of conformal time, it's a good point for giving you the condition under which the wavelength is equal to the Hubble rate. So this will play a crucial role in the following. Okay, so time to play again with this eraser. So in the rest of the course, we will see that the first thing to which determines the evolution of cosmological expression is the fact that it is larger or smaller than the Hubble space. This condition reads lambda coming from a physical wavelength equal to RH. I'm sure that you have seen RH in the last week or before. This is one of the two quantities with the dimension of space that you can build out of the Friedmann method. There is a spatial curvature, and there is a Hubble radius which stands for the radius of curvature with respect to time in space-time, RH and RC. So RH is C over the Hubble radius. Now let's rewrite this condition in Fourier space. We will introduce Fourier space with respect to comoving coordinate x, which means that a comoving wave number will typically read 2 pi over k. A physical wave number will be this comoving quantity times the scale factor. So this is the value of a given physical mode at a given time if it is described by the wave number k. This wavelength is equal to double radius when the arc is equal to 1 over h. I work in natural units. Okay, and so the condition can be rewritten as k. I just define k is of the order of ah, or I could write this as l prime over a. Okay, so the value of k larger than this corresponds to a wavelength smaller than the double radius. This was a little digression. Coming back to the Newtonian